right, let's get started. Today we're going to discuss VSEPR theory. This is in chapter 3.2 of the text. If you want a refreshment of your general chemistry concepts, I would encourage you to also read chapter 3.1. There you will read things like valence shell electron counting, Lewis dot structure, formal charge, calculation of lone pair. We're going to cover some of them in the following slides as well. VSEPR theory is called valence shell electron pair repulsion. It is an empirical approach to predict molecular geometry by analyzing electrostatic repulsion of so-called electron pairs. Now, as with all other empirical methods we have discussed and we will be discussing in the future, it works very well most of the time. I would say 95% of the time, especially for main group compounds. But there are indeed exceptions. Okay? Typically, those are cases where repulsion between different pairs become too complicated to analyze analytically. Now, the whole idea of the VSEPR theory is based on electrostatics repulsion. So an essential step in applying the analysis is to correctly count the number of electron pairs and to visualize and analyze their interaction in three-dimensional space. The overall objective of this class is to start with a molecular formula and end up with three-dimensional geometry of the molecule of interest. Okay. A brief background, we're going to talk about two things before we move on to the VSEPR theory. The first thing is the octet rule, which I believe most of you should be familiar with. It basically says that most main group elements will try to achieve 8 electrons in their valence shell when they form chemical bonds. The only exception is hydrogen in this case, which would only require 2 electrons to be stable. Now, this rule is useful when we try to predict the number of chemical bonds between the so-called ligand atom and the so-called central atom. We're going to explain what those two atoms are in the next slide. The next useful thing is the calculation of lone pairs in a particular atom in a molecule. Okay? Now, the calculation is done in the following way. We start with the total number of valence shell electrons of the atom, of the neutral atom. You subtract the number of chemical bonds it forms with other atoms, and then you subtract the number of charges. Okay? And you take the result, divide by 2, and that's the number of lone pairs this atom has. The idea here is very simple. Basically, an electron will only exist either as a lone pair, as part of a lone pair, or part of a chemical bond. So you take the total number of electrons in an atom, and then you adjust the electron counting by the formal charge on the atom, and then you subtract all the electrons involved in chemical bonding. That will be the total number of electrons involved in forming lone pairs. You divide that number by 2, you come up with the number of lone pairs. Okay. Couple of examples. For example, methane, for the carbon atom, you start with 4 valence shell electrons for neutral carbon atom. There are 4 single carbon hydrogen bonds. If you subtract that by 4, and there's no charge, so subtract it by 0, and then you take the result, divide by 2, that's 0. Okay. And in the other case, ammonium ion, for example, you start with nitrogen, neutral nitrogen, that's 5. There are 4 nitrogen-hydrogen single bond, so that's 4, and there's a positive charge, so minus 1. You take the result, divide by 2, that's 0 again. Okay. Now, one thing I want to emphasize here is that the number of bonds here refer to essentially the total number of electrons involved in forming covalent bond. So what that means is if you have a single bond, it will be counted as 1 bond. Now, if the atom forms a double bond, it will be counted as 2 bonds. Okay. Now this is different from the calculation we're going to do in the next slides or two. All right, now come back to the VSEPR theory. The overall approach is the following. You do a three-step analysis. In the first step, you calculate the so-called steric number for the central atom. Okay. Now the central atom is the atom that forms chemical bonds with all other atoms of the molecule. Okay. So in our discussion, we're going to limit our analysis to a relatively simple molecule in which there's one atom forms chemical bonds with all other atoms, and those all other atoms are called ligand atoms. Now, the steric number is it's very simple. It's the sum of two numbers. It's the sum of number of lone pairs and the number of so-called bonding pairs. Okay. The bonding pair is essentially electrons involved in a chemical bond. Now, lone pairs are invisible to us because we can only see atoms. Now, bonding pairs are invisible to us because there's always another atom associated with a bonding pair. Now, that in the next step, we're going to identify the ideal structure associated with the steric number that we calculated in the first step. Okay. Now, this will give us a geometry that corresponds to the lone pairs and the bonding pairs. Okay. Now, as I just mentioned, lone pairs are invisible to us. So in the final step, we analyze the repulsion between all the electron pairs, and we will come up with some kind of conclusion that involves geometric deviation. And we'll also get rid of the lone pairs from our discussion, and we'll come up with a geometry of the bonding pairs, that is without the lone pairs. Good. All right, some details for each step. The calculation of steric number, as I said, is a sum of bonding pairs and lone pairs. Okay. Now, when you do the calculation, you basically add up the number of bonds the central atom has, and add up all the and add all the lone pairs that it has. And we already discussed how to calculate the number of lone pairs on the atom. Okay. Now the number of bonds here, okay, is essentially the number of ligand atoms that form chemical bonds with the central atom. Okay. Even if you have a multiple bond, it's still counted as one bond. Okay. Now each lone pair is counted as one. There's no exception here. But in the first case, the number of bonds is, whether it's a single bond or multiple bond, is always counted as one. Okay. So if a molecule has one single bond and one double bond, the total number of bonds would be 2. All right, now once you come up with a steric number, you then look at this table. This table is the figure 3.8 of our text. And what you do here is you simply look up the table and find the corresponding geometry. Okay, so for steric number 2 is linear, 3 is triangular, 4 tetrahedral, 5 trigonal bipyramidal, 6 octahedral, 7 pentagonal bipyramidal, 8 square antiprismatic. Now if you look at the examples here, okay, what you realize is that all those geometries are formed such that the electron pairs would be as far away from each other as possible. Okay. Those are the ideal geometry that's going to make the structure stable. Why? Because all the electron pairs, they are essentially negative charges. Okay? So if you think from a simple electrostatic point of view, negative charges would want to stay as far away from each other as possible. And that's why they will, form those ideal geometries. Okay. Now, this is an ideal situation in which all the electron pairs are identical. If you look at the examples given here, okay, all the ligand atoms are identical and there are no lone pairs on the central atom. Okay, and that make it simple to analyze, but in reality, there are many other situations that are not that ideal. Okay, and for those situations, we have to do a third step analysis, okay? And that would be the structure deviation that could occur due to the non-ideal structure. So there could be other couple of things that is happening. One is that, and the most often is the presence of lone pairs in addition to bonding pairs. And there could also be a situation where you could have multiple bonds in addition to single bond. Okay. Now, the general principle we're gonna take is to simply think about electrostatic repulsion. Now, the structure should minimize electrostatic repulsion as much as possible. So if you follow this idea, okay, now you will come to some very simple conclusions. And one of them is that if there's one electron pair that is more powerful in terms of electrostatic repulsion, then it will push other electron pairs a bit further away from itself. Okay. Now, the order of electrostatic repulsion goes as the following. Lone pair is the most powerful, followed by multiple bonds, followed by single bond. Okay. And one way you can understand this is that lone pair is a bit closer to the core. Okay. So in terms of distance to other electron pairs, because it's closer to the core, it's a bit closer to other electron pairs as well. And lone pair is also more densely concentrated in terms of their charge because there's no other nuclei to pull the electron density away from the central atom. Okay. So following that analysis, you come to the conclusion that lone pair repulsion is the strongest, followed by lone pair and bonding pair, followed by bonding pair and bonding pair. Okay. And if you have multiple bonds, the repulsion from a multiple bond is going to be greater than that from a single bond. And the last step we're going to use an example to illustrate this is that in complicated cases, we're going to only analyze 90-degree interactions because electrostatic interaction falls off as 1 over distance squared. Okay, so as the two electron pairs are further apart, their interaction decrease even more, decrease as 1 over the distance of power of the distance. And that makes 90-degree interaction more important than, for example, 120-degree interactions. Again, we're going to look at this rule using examples in a moment. Okay. All right, now let's look at one simple example. We're going to look at ammonia. We're going to apply the 3 steps. First step is to identify the central atom and the ligand atom. Now, in this case, nitrogen is the obvious choice because each hydrogen can only form one bond. So you cannot imagine a case where one hydrogen atom forms multiple bonds with other atoms in the molecule. So nitrogen is the central atom, and in actually a lot of cases, the central atom is the first atom in the formula. Obviously, there are many exceptions like water, hydrogen cyanide, nitric acid, sulfuric acid, and many others. But there are still a lot of cases where the first atom in the formula is the central atom. Okay, so the key here to look at is whether the atom will be able to form multiple bonds, actually form all the bonds with the rest of the ligand atoms. Okay. And the next step is to calculate steric number. There are 2 things we have to do. One is to figure out how many bonds are there, and basically in this case is the number of ligand atoms in the molecule. So that would be 3 because we have 3 hydrogen atoms. And then the number of lone pairs for ammonium, the number of lone pairs can be calculated by starting with the number of valence shell electrons in nitrogen and subtract all the number of electrons involved in forming chemical bonds, and then adjust for formal charge on the nitrogen atom. So that would be 3 valence shell electrons minus 3 single bonds minus 0 because the whole thing is neutral, and divided the result by 2, that would be 1 lone pair. And you add up the number of lone pairs with the number of bonds, you come up with stellar number of 4. And if you look at the table, you realize, let's see the table. You see the ideal geometry is tetrahedral. Okay. Now, the example here with methane is highly symmetrical in that all the electron pairs are in the form of bonding pair. Okay. Now, that is not the case with ammonia, because in this case, there's 1 lone pair and 3 bonding pairs. Okay. And the result is that the lone pair will push the 3 bonding pairs a bit away from itself. So you will still have a roughly tetrahedral structure, but the 3 hydrogen atoms will be a little bit closer to each other than ideal tetrahedral structure would allow. Okay. All right, so that concludes the analysis of ammonia. In the next slide, I'm showing 6 molecules. What I want you to do is to pause the video for now and give yourself 10 minutes to work on the analysis of the 6 structures. And when you are done, you can continue the video, and we're going to talk about each one of the structures. All right, now get started. All right, hopefully you have finished all 6 in the 10 minutes of time. Now let's look at the answers to each question. Phosphorus pentafluoride, steric number should be 5. This is a case where the ligand atom has no lone pair because phosphorus has 5 valence shell electrons and form 5 bonds. So 5 minus 5, and the whole thing is neutral, so minus 0, so no lone pair. And steric number equals 5 because you have 5 ligand atoms. And you look at the table, you'll find is trigonal bipyramidal, and this is the case where all ligand atoms are the same and no lone pair, so it's the ideal trigonal bipyramidal structure. POCl3, steric number should be 4. Again, you look at phosphorus. Phosphorus start with 5 valence shell electrons, and the number of electrons involved in bonding are also 5 because there are 3 chlorine atoms, each require 1 single bond. The oxygen would require 2 bonds to fulfill its octet rule. So in total, you need 5 electrons from phosphorus to form 1 double bond and 3 single bonds. Okay? So 5 minus 5, again minus 0, because the whole thing is neutral, you end up with 0 lone pairs. And the number of ligand atoms here are 4, so total of 4 bonding pairs, 0 lone pairs, steric number equals 4. And this will be a tetrahedral structure overall. Now the ligand atoms are not all the same. Oxygen forms a double bond. You look at the structure on the right hand side, oxygen forms double bond with phosphorus, and chlorine forms single bonds. So the double bond will push the single bonds a bit further away from itself and makes the chlorine phosphorus chlorine bond a bit smaller than what you would expect from an ideal tetrahedral structure. So the bond angle is 103, smaller than 107. That is, 109.5. That is the ideal bond angle in tetrahedral structure. The next one, sulfur trioxide. This is the case where steric number equals 3. This is the example in the table, actually. Next one in line, triiodide. this is the case where 2-iodine is linked to a third iodine in the middle. If you calculate the steric number for the iodine in the middle, you end up with 5. Why 5? Because iodine has 7 valence shell electrons, and you subtract the 2 chemical bonds it forms with each iodine, because each iodine only requires 1 bond to fulfill its octet rule. So that's 7 minus 2. Okay. And then you have to adjust for the charge. This is a negative charged ion, so you would add 1 electron count to the total to the equation. So that would be 7 minus 2 plus 1. So that would be 3 lone pairs. Okay. So 7 minus 2 plus 1, so that's 6 divided by 2, that's 3. So 3 lone pairs and 2 ligand atoms, steric number equals 5. So that would be trigonal bipyramidal. Now there's a question of where do you place the 3 lone pairs relative to the 2 iodine atoms, and here we're going to invoke the third rule we discussed before, in that in complicated cases we can only discuss and count and analyze 90-degree interactions. Okay, so now if you look at the structure of triiodide, you'll find the structure here. Okay, this is actually the actual structure of I3 minus. The ideal structure has the 3 lone pairs on the plane and 2 iodine groups above and below. Now, why it prefers this configuration? Because in this case, the 90-degree interaction between 2 lone pairs are 0. There are no 90-degree interactions between the lone pairs. The lone pairs are 120 degrees apart. Okay? Now compare this configuration with an alternative in which the lone pair is in the axial location, in the place of 1 iodine here. And in that case, the lone pair will form 90-degree interaction with 2 other lone pairs on the plane. Okay? So that is not preferred, and this configuration would be preferred. Now going down, sulfur hexafluoride, this is steric number 6. This again is the example in the table, octahedral structure. There's no distortion. The last one, chlorine trifluoride. It has steric number 5, and this can be calculated by first identify the number of lone pairs in chlorine. So you start with 7, which is the valence shell electron for chlorine, minus 3, and you take the result divided by 2, and you end up with 2 lone pairs, and you add that up to the 3 bonding pairs, because there are 3 fluorine atoms in the molecule, so you end up with a steric number of 5. Now, the ideal structure for steric number 5 is trigonal bipyramidal, but this structure is not symmetrical in the sense that it has 2 lone pairs and 3 bonding pairs, so we have to think about where the bonding pairs are going to be. Now, if you look at the right-hand side of the slide, there are 3 possible candidates there are different ways of placing the lone pairs. In structure A, the lone pairs are placed on the 2 axial locations. In structure B, 1 lone pair is on the equatorial position and another is on the axial. And structure C, both lone pairs are on the equatorial position. Oh, by the way, the 3 fluorine, the equatorial position refer to the triangle shape in the plane, and the axial position refer to the top and bottom. Okay. All right, now if we look at each structure, what we're going to do is we're going to analyze 90-degree interactions of different type. So there's 3 types of 90-degree interactions. They're between lone pair and lone pairs, between lone pair and bonding pairs, and between bonding pair and bonding pairs. Okay, so if you recall the degree of repulsion we discussed, we want to minimize lone pair interaction at all cost, and the most preferred interaction is bonding pair and bonding pair, because their repulsion is the least intense. All right, now if you look at structure A and count the 90-degree interactions, and you will realize that the only 90-degree interaction are between the axial location and the equatorial position. Okay, so in this case, there are 6 lone pair, bonding pair interactions. If you look at structure B, in this case, there's one 90-degree interaction between lone pair and lone pair. There are 3 90-degree interactions between lone pair and bonding pairs, and 2 between bonding pair and bonding pairs. Okay? So 1, 3, 2. In structure C, the situation is much better in that there's no 90-degree interaction between lone pair and lone pairs. There are 4 90-degree interactions between lone pair and bonding pairs, and 2 interactions between bonding pair and bonding pairs. So the type of interactions are, the number of interactions for each type is 0, 4, 2. Okay, so if you combine all this, if you compare all the 3 analyses, you'll find structure C is the most favored, energetically favored, because it does not have any 90-degree lone pair interaction, and it has the maximum number of bonding pair and bonding pair interactions. All right, now in reality, structure C is still the ideal structure, because the 2 lone pairs on one side, they will be much more repulsive than the fluorine atom on the other side. Okay? So in reality, those 2 lone pairs will push the 2 axial fluorine atoms a bit away from the 90-degree location. So the experimental structure is more like a distorted T. It's not the straight T, in that the axial fluorine axial fluorine bond angle is not 180 degrees. All right, so this will conclude our discussion today. I will post more exercise examples onto CourseWeb. Please take a look at them after you finish reviewing this material, and try our best to finish as many of them as possible. Thank you, and see you in class on Wednesday.